All right. So, first comment before I forget, next two lectures are going to be on Zoom. So will not be in person. It's over there on the board. I totally forgot to announce it earlier. Sorry about that. I'll try to send a message on Brightspace. All right. So I'll start with a summary of lecture 5, and if there are any questions, do ask, please. So what we started doing last time was we did two things. First, we discussed examples of two-loop diagrams in lambda phi 4 theory. We saw that at least two loops for these diagrams that we considered. Counter terms cancel all divergences. We did not do the calculation really. I structurally showed you how you do it. You define these functions k1, k2, right? And you systematically keep track of them. The important thing about it, some of these lessons generalize nicely to higher orders in perturbation theory. For example, you have this type of diagram. By staring at this diagram, you can see the divergent structure of it, right? So the divergent structure of this last guy, this last loop, is lambda squared, right? The reason is that it has a 4 momentum in 2 plus 1 over 1 propagator. That's this diverges like lambda square. Lambda is a cutoff, UV's cutoff square. Whereas all of these other guys, they diverge like log, right? The reason is that if you have a something in the middle like this, there are 2 propagators and 1 loop. So you have D4 of P and a pair of propagators, right? So this is log divergent. So, and then similar arguments for this would work, and then you'll see the log divergence of structure of this guy. Then we completely switch gears and start talking about effective actions. So that's what's going to be the discussion of today as well. We're going to continue our discussion of effective actions. It is the build-up towards renormalization group. We started by building and working on the analogy between statistical field theory and between statistical mechanics and field theory. And so here's an analogy. There's quantum field theory. Here's classical finite temperature physics. We have a spin system. Then we coarse grain this, introducing some coarse grain averaged degrees of freedom. These are magnetization. And that's m of x. In the continuum limit, it becomes a smooth function of x. And then in the comparison is that on the QFT side, you have space-time fields phi of x mu. There's an external field in partition functions. That's how we deal with it. We apply an external field and then study the response, right? That's what the story of classical physics is. Finite temperature physics is. You study linear response, for example, or nonlinear response. Similarly, we do the same thing in quantum field theory by introducing sources, right? So there are fluctuations in the classical physics side. These are thermal fluctuations. The parameter that controls it is 1 over beta, right? That controls the size of the fluctuations. And in quantum mechanics, the fluctuations are controlled by 1 over h bar. Sorry, h bar. H bar. By h bar. Now, here's an interesting thought. Consider quantum the system. We're at finite temperature. The system is quantum mechanical and finite temperature. So it has a combination of thermal fluctuations and quantum fluctuations. But because temperature, or 1 over beta, or beta is temperature is a lot larger, the thermal fluctuations dominate, basically completely flood your analysis, and you don't need to worry about quantum mechanics. So when you start seeing quantum fluctuations as you turn down the temperature, you go to very, very low temperature. So the thermal fluctuations are characterized by a length scale. What is that in statistical physics? mean free path or something, right? So at some finite density, your particles propagate freely until they interact, right? And they scatter. So, and then there is the quantum fluctuation, which is the Broglie wavelength. When they become comparable is when you start seeing quantum effects kick in. All right. So back to classical physics, you deal with partition function. Partition function is what a physicist calls this a path integral over m of x magnetization with e to minus beta h plus, this is a source partition function. This is the source for magnetization, the external magnetic field, right? This is a moment generating function because you take derivatives of it and you get moments. Similarly, in quantum quantum field theory, you have the generating functional, which is a path integral over the field variable, of course. X, this is X. And then here's the action, and then you source it, you put a source. Now, beta controls the size of the fluctuations, right? 1 over h bar controls the size of the fluctuation. So beta is to be compared with 1 over h bar. H bar is to be compared to 1 over beta. What happens when beta is very, very small? When beta is very, very small, we're at high temperatures, you can, what happens? All right, think about that. Okay, I'm not gonna. All right. Good. We introduced the, well, in classical physics, we introduced the Helmholtz free energy, which is a minus log of the partition function. And this is the generating functional for the connected correlators. If you take one derivative and set b equals 0, then what you obtain is the magnetization, classical magnetization, 1-point function, right? Similarly, you can take the minus log of the partition function, or if it's the generating functional. If it's real time, then it's I log zj. This is the generator of connected correlators, and then you take derivatives with respect to j, and what you find is a 1-point function that we're going to call phi classical. Yeah.
Usually when it's real time, that's when the I.
Yeah, there's an I here when it's real time, right? Why is that? Because what is the what's the path integral in real time? Sorry, z of j is phi I s phi over h bar. So what you want to do is you want to write this as something here. What does that call it? I call it W. I W phi. W of j, sorry. Right? So you evaluate this generating functional, then you take the log of it and multiply it by minus I. Right? Now, last time what we talked about was the Legendre transform. This is when you take your Helmholtz free energy, and add to it MB, then you've introduced something that's called Gibbs free energy in thermodynamics or statistical physics, and it's just a simple set of derivatives, just calculus, to show that the variation of the Gibbs free energy with respect to magnetization is the source, is external field. What does that tell you? Similarly, you could do that. What does that tell you? It tells you that if you set b of x equal to 0, then the Gibbs free energy is extremized on the classical expectation value, right? On the 1 point, the value of the magnetization could be read off by looking at the extrema of that gives free energy. What happens if there are a couple of extrema? This is important. Just think of this example, classical physics. Yeah, well, what happens when there are a couple of extrema? Free energy. When you have a classical system, there's a free energy, and what happens if there are two extrema of free energy? The one with the minimum wins. Why? Oh, minimum free energy. It's not energy, it's free energy. The reason is that when you have several saddles, so here let's go to classical mechanics. So what you have is this m of x e to minus beta x plus da da da, right? So what happens when you look at the in the thermodynamic limit, what happens is that you use saddle point approximation to approximate this, right? And when there will be different saddles contributing to this, so there will be different saddles contributing to this. Each of these are extrema. I'm just talking free energy for now, right? Each of these are extrema of the free energy function. Now, so it's pretty clear that if there are two saddles, the values of them might be different, but there's an exponential suppression between them. So the one that is subdominant is contribution to the partition to the free energy is exponentially smaller. So you only pick the smallest one. And in the thermodynamic limit, free energy is extensive, so this blows up, right? So you only pick the minimum one. All right. Similarly, what you do in quantum field theory is you define effective action, which is you take you do the Legendre transform of your Helmholtz free energy by adding to it Legendre transform of the moment generating functional, Q-Millen generating functional, but adding to it integral of j of x phi classical of x, right? This is a functional of phi classical, right? The phi classical is just some variable, some function. Now, of course, the same rules of derivatives apply, and you obtain this equation, which tells you that if you do the calculation, set the source equal to 0, then effective action, this function, is extremized on the classical equations of motion, on the classical solution, on the 1-point function phi classical. Today, what we're going to see is an interesting property of effective action, that it's the generating functional for the 1-pi diagrams. So do you remember what 1-pi diagrams are? They are the diagrams that if you cut at one point, any line at the point, they will not split into two disconnected pieces. Right? Sorry? Yeah. So there are the connected versus disconnected. Right. So the connected ones could be thought of as a 0-point irreducible. There's 1-point irreducible. You could also generalize this analysis to 2-point irreducible, but we're not doing any of that. So 1-point irreducible is important for us because the generating function of it is going to be the effective action. But those were the calculations we were doing. Remember where the 1-point irreducible diagrams appeared. Like, for example, the renormalization propagator. we resum them, right? When we looked at the full correction to the propagator, this was 1 pi. Sorry, this is this plus 1 pi plus 1 pi, 1 pi, and so on and so forth. And this will resum as 1 pi. Right? So similar structure applies for resummation of all our full diagrams, right? So when you have any other diagram, like let's say you have a diagram like this, some sort of interaction. Well, let me do a 4-point function. So you can view it this way. You can think of terms like this appearing in there, right? Yeah, okay. But we're gonna do similar things here. So the 1 pi generating functional, the generating functional for 1 pi diagram is going to be phi classical. So here's the derivation. We're gonna do that today, and another thing, but then we're gonna switch gears and talk about something else. All right. So this is the equation we're starting with. We're starting with this, right? The variation of the effective action with respect to phi classical is j of x. So if I take another derivative variation, if you vary this with respect to jy, what do I get? I get a Dirac delta function. Good. So if you get lost at any point, let me know. Okay. So this equation is good. All right. Very good. Now, what do I do next? I take this derivative and write it as follows. I write del j as del phi classical del j del phi classical. Okay, so I've added this. So this thing is this thing, right? I put this guy. So this is y. I put this guy at z and integrate over it, right? Because of this. So del j is an integral over d of z. Good. Okay. Now you notice that phi CL itself is minus del W del JZ. So this term is del JY minus del W del JZ. Good. What is that? That's the connected 2-point function with J in there. I've not set J to 0 yet. In the presence of J, this is what the connected 2-point function is, because this is the second derivative of W. Good. So what do we learn? Putting these together, we learned that the Dirac delta function is an integral over z, the connected 2-point function, the second derivative of the effective action with respect to the phi CL. So what was this all about? Well, I started with phi CL, gamma of phi CL, took the first derivative with respect to phi CL and saw this is j. Right? Now I'm calculating the second derivative. What does this equation tell you? This equation says that the second derivative of effective action with respect to phi CL is the inverse of the connected 2-point function. Right? When this integrals to Dirac delta function, it means this is the inverse of it. Differential inverse, right? So schematically, we could write it this way. but this is a equation. Good, everyone's with me? All right, what am I gonna calculate next? I'm gonna, so we found the second derivative. And this was the connected triangle, the presence of J. Now we're gonna calculate the third derivative and higher derivatives. I'm just gonna do the third derivative. It gets more and more complicated, but you could see the recursion in it. Good. All right. So write it this way. The 2-point function with J connected is the inverse of the second derivative of phi, of effective action. Consider the 3-point function with the connected piece of three. Oh, actually, no. Consider the 3-point function, the connected piece of it. What is this? This is just a derivative of this guy. Because these are derivatives with respect to J of W, which is the generating functional for the connected correlators, right? So as I take derivatives, I keep saying that. But the logic here is also pretty clear, right? So I'm going to repeat that. I erased it. So del JW, I'm going to write it, insert this thing and integrate over it. Good. But then I notice again that this is just a 2-point function, connected 2-point function. Now, what is this? The rest of it. This could be written as this guy minus 1, this minus this. Can you see why this expression, why this derivative is this? Can anyone see that? It's a rule in your calculus. You must know this. This is extremely important. You know it probably. What do you have? Okay, if I have x minus 1 du, what is this? This is 1 over, this is x minus 1, the x minus 2 dx du, right? What if this is an operator? What if it's a matrix? What if, so this is x of u, right? What if your x is a matrix, d du, and you're taking derivative of the inverse matrix? What happens is that this is going to be x minus 1 dx du, x minus 1. It's x minus 2, but because these are matrices, it's symmetrized. This is a fact. This is just linear algebra. Can you see it now? This you should know. If you didn't know this, you should use it all the time. It's all over the place, everywhere. Good? All right. So what did we find? We found that the 3-point function, connected piece of it, is an integral. So now what are these? This is also a 2-point function. This is also a 2-point function. A connected 2-point function, connected 2-point function, connected 2-point function, and the third derivative. This is the equation we have. Is everybody okay with this equation? Do you see where everything comes from? So previously, in the previous step, yeah, that's good. In the previous equation I had, what I had was I wrote the Dirac delta function as an operator multiplication, like integral over the connected 2-point function multiplied by the second derivative. Then I interpreted that as the second derivative is the inverse of this. So let's draw a picture for this. What is the left-hand side? Let me just actually go up here. What is the left-hand side? The left-hand side is a connected three-point function. What's the right-hand side? Well, this is this part. This is this part. This is this part. This is 1pi. This is a fact. That the connected three-point function could be written in terms of diagrammatics. Connected two-point functions here and the 1pi. Now, the interpretation of that is obvious, right? That guy is nothing but the 1pi here. Good? Now, repeating this for the 4-point function, I'm just going to structurally tell you how it works. What happens is that there are these diagrams. So 4-point function admits this could be written this way, where this is the one, well, very good. 4-point function could be written this way, plus this way, plus the two other channels, diagrammatically. Now, what do? You start with the previous equation that I had. So what you do is this. You write down the 4-point function, j connected, as del j of the 3-point function j connected. You plug in the previous expression. In here, you write this jj as an integral over da da da. You expand it, you do the differentiation, everything, you treat it right, and you reproduce this picture where the fourth derivative sits here. These are the three derivatives, and so on and so forth. So the fourth derivative is the 1pi diagram. So the n-point 1pi diagrams is the nth derivative of gamma. This was not proof. This is diagrammatics demonstration. And you'll have to work a little bit harder to prove it. But hopefully you see it, right? That's why we love the effective action so much. So if somebody gives you the effective action, they have given you all the 1PIs. You know everything about that quantum field theory. You know everything about it. Questions?
So effective action is kind of like we just use the original passage. We would get like we know we have a 4-point function, and we have to do like expand and get its one loop fraction, second loop fraction, and by the effective action we just simply get the 4-point thing.
Right, but there's no shortcut to it. To get the effective action, you have already done that. So how did I define the effective action for you? I said take W of j.
So we have to do the expansion first.
But
and then
yes, but somebody does it once, and you're good. Right? Somebody gives it as a functional to you. And you're good.
So like it's just a way to pack all these things.
It's a very intelligent way of packing all of that. So somebody can calculate the moment generating functional as well and give it to you, right? Then you know everything about the theory as well. But then it's a little bit more, like if you're doing some diagrams, you might want to have more of a refined information, right? So for example, it's the generating function will give you the correlators. That's everything. Why do we even define W of j? Because to go between the moments which are between the moments and the connected moments, you have to use these Bell's polynomials. Is complicated. So there's a quick way of doing it. Now, if you're doing a calculation and you need the 1PI diagrams, right? To extract that from the W, from the correlators is hard, but from W is straightforward. But I do want to say that effective action is as close as we get to an action for a quantum system. It's the thing that when you vary, is extremized on the 1-point function with all the quantum corrections included. That's why it's called effective action. Now, this is not just an analogy. We're going to see explicitly how this is a building, like this builds, the whole idea of a normalization group is built on this. So everybody is good with the idea that, okay. All right. No, I'm going to pause here for more questions because there is a little bit of a change of topic going forward. I'm still going to use effective actions, but I'm going to do something a little bit different. How comfortable are you guys with spontaneous image breaking thermodynamics, StatMech? Okay. These statements, do they make sense to you? So 1D Ising model. Is there spontaneous image breaking? Yeah. So what is it? All the spins up, all the spins down. What are those states? Those are the vacua, right? These are the temperature. At finite temperature, there is no spontaneous image breaking. The moment you turn on one-dimensional Ising model, the moment you turn on smallest thermal fluctuation, tiny thermal fluctuation will break the vacuum degeneracy. That's good. This is called proliferation of. Anyway, it's easy to explain. In two-dimensional Ising model, what's the situation in 2Z Ising model? Do we, at 0 temperature, do we have spontaneous symmetry breaking? We do. We do. What if you turn on temperature? Okay, these are very important. This is like this really predates quantum field theory, and there's like a lot of ideas of quantum field theory built on this. In 1+1 and 2 dimensions, sorry, this is classical physics. In 2 dimensions, there is a phase transition below which finite temperature phase transition below which you have spontaneous symmetry breaking, and above it, like there's no order. Good. Okay, so I'm gonna say that a little bit again. So in Ising model, here is your your action, your Hamiltonian. Sorry, we're back to classical physics. So you have these are spin variables, and the Ising model could live on a lattice of different dimensions. These are nearest neighbor. The system has a Z2 symmetry. Si going to minus Si in arbitrary dimensions. Right? That's obvious from this. But the ground state breaks this symmetry, spontaneous symmetry breaking in 1 dimensions. It's either up or down. The ground state breaks it, right? And that means what? That means non-zero magnetization. What is magnetization? Magnetization is the average version of this. At infinite temperature, of course, there's no order. And it turns out that at any finite, at any finite temperature, what happens is that the order is destroyed. So there's no phase transition. Phase transition would be as we dial beta, there is a critical temperature where the order is changing. However, in 2 dimensions, that's not the case. At finite temperature, there is a critical temperature Ising model, right? Inverse temperature, critical temperature. And so What is M of X called? M of X, magnetization, is non-zero when you have order, right? It's zero when you don't have order, right? What is it called? It's called an order parameter. It is what you use it is to tell classical Landau's theory of phase transition. I don't know if you guys ever learned this, but it's an order parameter. You tell a phase transition is occurring, right? Which side of phase transition you are on based on the order parameter, the expectation value of the order parameter. Okay, in quantum field theory, this can also occur. There's also Z2 symmetry in these QFTs we've been talking about. It's a scalar field, right? Very similarly, there's a Z2 symmetry. The systems with the vacuum we've been talking about didn't break the symmetry, right? The 1-point function was 0. This is the order parameter. Phi classical is the order parameter. If there is spontaneous symmetry breaking, this phi classical would be the order parameter for it. Good? Hence, that's why I'm talking about this. So in lambda phi 4, we saw that, of course, the 1-point function is 0. Now, to cook up a more interesting situation, start with this Lagrangian. Sorry. Imagine your mass is negative, but then you have a lambda phi 4 term with a to make sure with a negative sign to make sure there's with a positive sign to make sure that's lifted, and you end up with this. So this is your potential, right? When phi is very, very small, this is negative. This term is large. This term is dominant. When phi is large, this term is dominant, so you go up. And this configuration, this potential is symmetric under phi going to minus phi, right? So it's like this, which tells you that it also reaches 0 at the center. Now, if this is the classical, this is the action, this is the potential, classically, there are two minima. There are actually three minima. There is this, well, there are two minima, sorry. There are two minima. There are three extrema. This is the maximum, is an extremum point, and these two minima. Good? The classical minimum of the potential is at these 2 points. Square root of 6, I believe, over lambda, yeah, because I put 4 factorial here, 6, over lambda mu that I'm going to call plus minus v. This is all classical physics. It's what spontaneous symmetry breaking is about. Good? All right. So what do we do? What we're going to do is the following. Imagine, so what if, so here's how it's going to work. This is a classical picture, right? And your field is a quantum field, but it's acquiring a 1-point function, right? If that 1-point function is 0, you could just treat the whole field and quantize it. If that 1-point function is non-zero, it's easier to separate the 1-point function and let the remaining piece fluctuate. Why is that? When we quantize field theory, this guy was 0. Why was that in canonical quantization? Because this is A plus A dagger in the vacuum. Of course, that's 0. Now, if I want to give this a 1-point function, how do I do it? What I do is I introduce my what I do is that I take my field and write it as some phi classical plus some other thing. This, what they call it, sigma or something. Now, this is the guy that has the accretion annihilation operators. Right? Now, with this language, I'm quantizing my field around this point. Good? You could even, I don't even have to say these things. You could deduce it all from the path integral. But so we're gonna write 5x as v plus some sigma of x. Now, we're gonna put this field redefinition, if you wish. I put v as being x independent, right? But I could take it to be x dependent as well. That's more complicated. Let's not do that. So you plug this in to the original action. This is what you obtain. You get half mu squared v squared minus lambda over 4 factorial v4. This is all a constant. This is a constant shift of the Lagrangian. It's a constant shift of Hamiltonian energy. Your energies are shifted. Plus half del mu sigma squared. Okay, that's the standard kinetic term for this field. That's good. Minus half 2 mu squared sigma squared. The mass of this field is not up to you. It's fixed by the initial Lagrangian, of course, by the parameters of the theory. Plus square root lambda over 6 mu 5 sigma cube. So you get a cubic interaction for this. It's a scalar field with a cubic interaction, but that's not the whole story. Lambda over 4 factorial sigma 4. Right? So this theory will have a 3-point interaction, 4-point interaction, right? Now, if I take this Lagrangian and plug it into the path integral, well, there will be a constant piece and then a fluctuating piece. I'm doing a path integral over field phi, so I can just do a path integral over sigma because these are constants. This comes out as a piece. What is the effect of this? This is a shift of W. What is W? It's log of this partition function. So this is a shift in W. What does that mean? Well, okay, I said what I said. Good. All right. Is this all good? There's a lot that I talked about. This is spontaneous symmetry breaking, the simplest example possible. Why am I talking about this? Because I started talking about phi classical 1-point functions. That seemed to be in contradiction with what we were talking about before. In canonical quantization, the 1-point functions were always 0 due to Z2 symmetry, right? These are all consistent. I could expand around a different minimum, and that's what I'm doing here. Questions? All right. Now, what we're gonna be doing is linear sigma 1. So far, what do you know? In terms of models, we talked about lambda phi 4. We talked about gauge theory. Lambda phi 4 is not a nice theory. We'll see that. Well, we could perturbatively normalize it, maybe up to a certain loop, but there is not much of a deeper structure that will tell us about the non-perturbative aspects of the theory. We'll see. That will actually give us help. What is gauge theories turn out to be nice, and so do linear sigma models. These are models where there is a symmetry that tells you the theory is going to be good non-perturbatively. So the symmetry is the thing that is the tool that tells you that. So let's see that. Start with an ON model. So you have a field, vector field, a real vector field, n-dimensional. The action is del mu phi a squared plus half mu squared phi a squared minus lambda over phi 4. This is the action, right? It's familiar, hopefully. It's the ON model. Why is it called the ON model? Because under orthogonal, it has the ON symmetry. If you send phi a to R B A phi a, with R transpose R equal to identity, this is a symmetry of this action. So for example, O2 will have this symmetry. You could take phi 1 and phi 2, you could do rotations. Higher dimensional is just some sort of a funny thing. Good. ON, not SON. ON. All right. Very good. So now let's talk about spontaneous symmetry breaking. What does the potential look like? The potential looks like this Mexican hat. Right? This is the potential if you plot it. So the minimum will be achieved at somewhere here, right? So on some fixed radius. But all the point, the direction of this vector doesn't matter. That's arbitrary, right? Under an ON rotation, I could just move this around. That's not physical, right? So I can pick this to be in a particular direction, my favorite direction. So what do? What is the vacuum, classical vacuum? Phi naught of A, this is what minimizes the action. What minimizes the action is that 0, 0, 0, 0, V. I pick the direction, this, and I put it in this direction, V. The nth direction. And V is mu over square root lambda. Now I write my field as V plus sigma x. This is fluctuation in that direction. And pi k of x. These are the perpendicular directions. And minus one of them. Good? So now we're going to take this vector, plug it back into the action, and expand. We're going to get a constant piece plus a kinetic term for pi k, plus a kinetic term for mu, plus a mass term for sigma. Sorry, for a kinetic term for sigma. A mass term for sigma, but notice that there is no mass term for pi. I'm just plugging it in. There's no mass term for pi. Minus, this is a cubic term for sigma. There's a linear term. Oh, sorry. This is an interaction of well, we'll see it. 2 pi and a sigma, they interact. There is a sigma 4, pi 2, sigma 2, and pi 4. The lesson from this exercise is that pi k remains massless. ON symmetry is spontaneously broken to ON minus 1. In this picture, you had the O2 symmetry that's broken. Well, actually, yeah, I did not say that. Yeah. That's an exception. To ON minus 1. It's actually true, but anyway, I don't want to talk about topology. Good. Goldstone theorem. It tells you the following. Every time you spontaneously break a continuous symmetry, you get massless scalar fields. So let's go back. What are we talking about? Remember Noether theorem. Noether theorem tells you that every time you have a continuous symmetry in your Lagrangian, you have a conserved current. Here's a conserved current. What does it mean to have spontaneous symmetry breaking? This is classical physics. It means that del mu J mu is equal to 0, right? So the current is conserved, but the vacuum is not invariant under the symmetry. That's generically the case, actually. In this room, the equations of motion that govern this room are relativistic, but this room is not rotation invariant. The vacuum, my state is not rotation invariant. That's pretty obvious. It's not even translation invariant. I hid this, right? This is not the vacuum, right? But states can break it. When the vacuum breaks it, actually, spontaneous symmetry breaking can occur at finite temperature as well, right? So it doesn't have to be vacuum. If the state breaks your symmetry, we have spontaneous symmetry breaking. So Goldstone theorem tells you that for every generator of a symmetry, these are Lie groups, right? For every generator that you break, you obtain one massless mode that's called a Nambu-Goldstone boson. It must be a bosonic mode. We'll have the boson statistics, bosonic statistics. Well, we're not talking quantum mechanics yet, but we'll see. So for example, ON, how many generators does it have as a, how many generators does it have? It has n times n minus 1 over 2, right? You break it to ON minus 1, that has n minus 1 over times n minus 2 over 2. That means that there, if you subtract them, you have n minus 1 modes. These are the Nambu-Goldstone modes. What are these modes? These are pi k's. How many of them are there? N minus 1. This is actually a theorem. We're going to prove it or argue for it. Clear? Classical. This is all classical physics for now. The important point is that it survives quantum mechanically as well. Questions about this? Nambu-Goldstone boson.
Assuming nothing really changes if it's a complex variable,
The theorem is full general. It doesn't even assume the matter content. If you have some Lie group with a certain number of generators, you break it down to a smaller one, right? The number of generators that are no longer preserved, for every single one of them, you're gonna get a massless mode. Yeah. But what are you asking? Because complex scalar field is O2, right? Questions? All right. Let's quantize this action. This action, we didn't write it down. As opposed to, I want to emphasize this, as opposed to lambda phi 4, where I just wrote down an action, here I did not write down this action. This with all sigma 3 terms and these weird interactions. What I wrote down, I started with an ON theory and wrote down the first few terms. The symmetry is the crucial idea here. The symmetry is what saves me. We'll see. So here's what the action looks like. So let's draw the Feynman diagrams for it. So there's a propagator for the field pi that I'm going to draw with one line. Keep in mind that this is a vector. It's an n minus 1 vector. So, and the propagator for it is I delta ij over p squared. It's massless. It's boson. Good? That's a propagator. The sigma field, there's only one of them. And it's massive. Its mass is this, right? So here's a propagator for it. I start with ON model, so my sigma is also scalar. I have, sorry, sigma cube. That is sigma cube. I have pi 2 sigma. This is pi 2 sigma. I'm writing this in terms of V. See, remember there was a relation square root of 6 over mu or something with V. So I'm writing things in terms of V. There is a sigma 4 term. And then finally, well, there's a pi 2 sigma 2 term. There's this. And then there's a pi 4 term. This guy. These are all the Feynman rules. We just read them off. Good. And the coefficient, the important point is this. The coefficients you do not decide. They're given to you. That is what saves you. I cannot emphasize this enough, but I'll come back to this after I teach normalization, and we'll see that again. Because at the moment, it's not quite clear why I'm emphasizing so much. All right? So what are we gonna do in the remaining 15 minutes? We're gonna do renormalized perturbation theory for this. Why do I want to do this? Because I want to show you guys that at one loop, there is no correction to the mass of the Goldstone boson. It remains quantum mechanically massless. Okay? That's the plan. But it's also, we're still in the part of the course that's renormalized perturbation theory. Is another example. It's a little bit more elaborate than the one that you're familiar with. Not terribly complicated though. All right, so what's the first step of renormalized perturbation theory? For your field, you introduce a renormalization parameter. Can you put this to depend on A? Can you choose this to depend on A? Cannot. Why? It breaks your symmetry, ON symmetry. Right? You would not be able to write it as an ON renormalized action if you make it depend on A. So you could put it there and then conclude. So once you solve everything, you conclude that it has to be equal. There will be an equation that will tell you that, but in advance, you could just see that. All right, and then there are three, well, then you write this as L of R plus L counter terms, and there are counter terms associated to Z, counter terms associated to lambda, counter terms associated to mu. Here is now important, the important thing. What the main reason I'm doing this is the following. In the example of QED and the lambda phi 4, you had many counter terms. In QED, you had 3 counter terms and 3 vertices that you had to renormalize, right? So the number of counter terms seem to be matching. Here, you only have 3 counter terms. Sorry, not counter terms. 3 coefficients like this that you're going to fix, but you have many, many diagrams. So this is where the non-triviality of the theory comes in. A priori, it's not at all clear that it's going to be renormalizable. Renormalized perturbation theory will work, but you will see that exactly for these values of coupling that you did not choose, these are related. The coefficient of sigma 3 and sigma 4 are not arbitrary. As a matter of fact, if you put them arbitrary, you're going to get nonsensical theory. Those theories don't exist, right? These are given to you because of the symmetry. That's the principle, and that's what's going to save you, and you're going to obtain a theory that's actually renormalized by one loop. Actually, if you pick them to be different, it might end up being renormalized by one loop, but the non-perturbativity theory would not make sense. But we're going to get there. All right, so what are the counter terms? Diagrammatically, there is now a 1-point function for sigma. Right? There's 1-point function for sigma. There is 2-point function for sigma. There is, oh, sorry, wait. No, that's correct. There is 2-point function for pi. There is this guy, and then there is this guy. These are your counter terms. Oh, there's more, sorry. There's this there's this term, there's this term, there's this term. These are your Feynman rules. You just have to expand it term by term. You see, I repeat again, the coefficients of these guys are related. All right, so what are your renormalization conditions? The 1 pi of sigma will have to be 0. Good. The 1 pi for the propagator, its derivative has to be 0 on the mass shell, on the mass, physical mass. And then you have this condition for the 4-point function. These are the normalization conditions you have. Nothing else. All right. So let's look at this. Let's look at the this one PI diagram. What is this? Well, there's this diagram we could draw. There is this diagram we could draw, because you had pi 2 sigma. Sorry, yeah, pi 2 sigma was the term. This is sigma cube, and this is sigma. These should be, wait a second, I'm kind of confused with sigma pi. Yeah. Right. Okay. These should be 0. Now for the propagator, you're gonna have this diagram, this diagram, this diagram, this diagram, this diagram. This is the counter. You have to add them all. And then you also have these guys. So the important thing, observation here, is that if these 3 cancel, so do these 3. Do you see it? Because these 3 diagrams are the same as these if you add something here. Right? There are all sorts of interesting rules that you discover when you try to renormalize this perturbatively. Now, the important part for us is these diagrams. What are these diagrams contributing to? These 4 diagrams. These are the 1 pi terms for renormalization of the propagator of pi fields. This is what you need to check to make sure that your pi fields are your Gold-Sum boson, Nambu-Gold-Sum boson. This is what you need to check to make sure that your mass of your Nambu-Gold-Sum boson are not renormalized. These are 4 diagrams that you have to add and see. After you do renormalized perturbation theory, this is all fine, and they will cancel. And it does happen. So you can read about it in Peskin. We don't have time to reproduce that here, but at least I gave you the context for reading that discussion, that the Nambu-Gold-Sum boson classically is massless, is a consequence of the symmetry. The number of them is the number of generators you've broken. If you're going from ON to ON minus 1, it's N minus 1. It's a vector field. It's massless. And if you want to make sure that it remains massless, you have to do renormalized perturbation theory. For what theory? You start with your ON symmetric action. You expand it around some symmetry broken vacuum. You write down the Feynman rules, right? You renormalize the theory. Everything is worked out. At the end, you have to add up these diagrams, these 4 diagrams, and see what they add up to, and 0. For all of this to work out nicely, these values were important. These coefficients, these relations between these interaction terms were important. They were not, you did not come up with this. It was given to you by the ON symmetry. Let's say you don't know about this ON spontaneous symmetry breaking. You're a low energy observer, right? And all you know is that you looked around. Let's say you have an O2 model, right? So that you have 2 scalar fields. You write down an action for the scalar field. You write down a kinetic term for this guy, a kinetic term for that guy, a math for both of them. You write down the cubic term, 4 term for each of them. You might get something nonsensical. However, for these magical values, the theory was going to be nice. And the origin of this is that it's coming from a symmetry at higher energy scales. At this point, it's not that magical, but we're going to get to nonlinear sigma model. That's when things get very, very interesting. The reason is that I still wrote down an action for the ON model. But when we get to nonlinear case, it will be even more interesting. All right. Any questions? So the Nambu-Gould-Sum boson remains massless in quantum theory at one loop. In fact, it remains massless to all orders in perturbation. Jeffrey Goldstone is still an active faculty at MIT. You could go and talk to him. Any questions? All right. Not. Thank you so much, guys.